All right, well, welcome back to Fluids. Uh, Today we're going to talk about Archimedes' Principle. Well, Archimedes' Principle uh, has to do with the force, the buoyant force, on a submerged object. Well, whenever I hear the word force, I think about a free body diagram. So let's say that we've got a boat. And this boat, let's make it a raft. This raft has a certain weight. Weight of the raft. And let's put some people on the raft. And then you've got weight of the people. Oh, this is a short person. So we've got weight of the raft plus weight of the people. Yet the raft is not sinking. So there is some force pushing back up. Now if this raft were sitting on ground, what would we call that force? We'd call it the normal force. In water, we call it the buoyant force. Now the buoyant force is equal to, so here's Archimedes' principle. The buoyant force is equal to the weight of the fluid displaced. The weight of the fluid displaced. So basically what you have to do is you have to calculate the volume of the container, in this case the raft, that is underneath the water line, the volume that is submerged. And if you take that volume times the specific weight of the fluid, so the volume submerged, spell it all out, times the specific weight of the fluid. Let's try units there. Feet cubed, pounds force per foot cubed. Well, we're going to get a unit of force, and that is buoyant force. It's as simple as that. You figure out how much volume of the object is under the fluid line. In the case of a raft that is partially submerged, you just take that part that's under the water line. If it was completely submerged, you'd take the whole volume, and you get the buoyant force. There it is. Here, put a box around it. Archimedes' principle. Now, if we want to increase this and have just a little bit of fun, let's see if we can derive it. Don't hear those words come out of my mouth very often. So let's take a container of fluid. Let's use water. And let's take some box and fully submerge it. And there's going to be some pressure acting at this depth. Now pressure in a static fluid acts in all directions. There's definitely going to be some pressure will be acting down on our object. And then if we go to the bottom surface, whatever the pressure is there will be acting up. So pressure on the top surface, pressure on the bottom surface. Now let's take our object and say that it has some area, same area, top and bottom. So the force down will be pressure on the top times area, and the force up will be pressure on the bottom times the area. Then the net force, which is going to be the force up minus the force down. This is also the buoyant force, isn't it? If this object is submerged and it has some force pushing up, that's the buoyant force. So, equals the buoyant force. Yeah, very cool. Let's see. Let's put some distances on here. Let's call this ZB for bottom, and let's make this ZT for top. And then the force up would be, let's do it right here. The force up will be atmospheric. So the force up will be atmospheric pressure plus gamma ZB minus the force down, that would be atmospheric, plus gamma gamma ZT. Okay, now I have pressures here, so if I take all of these pressures times the area, now I'm going to have the force. So what I have is the net force will be the force up, which is pressure atmosphere plus gamma ZB times area, minus force down, which is pressure atmosphere plus gamma ZT, get rid of that, there's nothing there, times area. And this is the net force. I also said it was the buoyant force. Let's see. I think that the atmospheres can cancel. And let's see here. Wouldn't ZB minus ZT, wouldn't that just be the height of the object? Let's use H so we don't get confused with all the different Z's. I think ZB minus ZT is the height of the object. So really what I have left here is gamma times ZB minus ZT times A. But this is really gamma times H times A. Hey, wait a minute. Isn't that the formula for volume? Area times height? It is. So the buoyant force, which is just the net force due to the hydrostatic pressure on the bottom minus the hydrostatic pressure on the top, those two forces give us Archimedes Principle. There we go. Boom.